Good morning to all. This is Anvesh from Triple Branch. Uh, so today my topic is about the Samsung M3 processor. So let's get into it. So, firstly, the Samsung M3 processor, the competition for a mobile smartphone is adding performance at a rapid pace, and the design team at the Samsung Aston R&D is determined to respond, building upon the first generation MI design that was preparing for a tap out in late 2014. The initial planning for subsequent generation micro architectures started in Q2 of 2014. The second generation M2 was originally planned as a shrink of the MI RTL work for the third generation M3 began starting in QI of 2015. By Q3 2015, it became clear that Samsung could operationalize improve M2 by pulling a subset of feature from the next generation. The third generation M3 goals were reset to much high bigger targets. The M3 processor is designed for the flagship Samsung smartphones, building upon the prior designs. The M3 has winded the bandwidth depend the out of order window and improved lattices in both core operations and cache harnesses. The result launched early in 2018 and fabricated in Samsung 10LLPP processor technology is a higher competitive design that achieves higher performance with efficient power expenditure. So now the Samsung M3 processor goals are the performance goals of the recent M3 program were to push up IPC on a board set of workload with the available schedule without losing frequency versus the prior generation. Power efficiency was prioritized over absolute power. Area growth was a concern, but applicable if good performance gain could be shown. The performance analysis effort for the M3 processor was broken into three phases, each of which requires different abilities from the analysis team. Early uh, trailblazing features mining, implementation trade-offs, and final correlation polish. In reality, the analysis phase for M3 were not crisply defined, and the coloration phase of M3 completely overlapped the trailblazing phase of the next core M3 M4, just as a correlation of prior design overlapped with the begin of M3. For the M3 processor performance effort, workloads that span both the current mobile ecosystem and industry standard CPU benchmark were used. For the mobile side, core benchmarks such as Geekbench V4 and ANU were chosen, as well web system benchmarks like Octane, SunSpider, BBBench, and BrowserMark. These were augmented with the internal real-world mobile workloads from the CPU industry side. Drystone, Core Mark, SPU, CPU 2000, SPC, CPU 2006, and other were analyzed. Note that this workload collection was constantly evolving during the M3 program as new compiler or library drops, workload revision, and new benchmark were released. Due to early critique of mobile processor market, the analysis team continued to look into deficiencies of predecessor design throughout their design timeline using a cycle accurate simulator. Any insights that could not be corrected in M1 and M2 family due to schedules or area had been put on the shelf for consideration on M3. The team had also been building a long-term roadmap for of more ambitious microarchitecture improvements which might take years to reach their final evaluation. Performance modeling of several of these features began during M1 and M2 projects. As soon as the primary focus could be shifted to M3 processor analysis, there was a large backlog of ideas and partial module implementations to sift through. Early in the entry discussions, it was decided to widen the machine to 6 weight throughout. Additionally, the depth of the out of order window was grown, anchored by a target record buffer size of 228 entries. These large increases in the width and depth was chosen based on a mix of what was showing sufficient promises on IPC increase while still being on the edge of what a design team through was buildable at frequency targets. The M1 and M2 has been balanced for about 4 wide cores and 100 entities ROB, so that M3 has to be rebalanced for the 50% growth in width and more than two depth. This requires a series of studies for all the major resources in the machine. Due to this interconnected relationships of these resources, it took an iterative approach to collectively tune all of these given the timing, area, schedule constraints. The M3 processor core microarchitecture. The M3 implements a RMV8A2. This shows an overview of M3 core microarchitecture, which is a 6 wide out of the order design. The core features 64 KB LI caches, advanced dynamic branches, predictors, and an aggressive data prefectures, while the sustained instructions per cycle is 6. A peak of 11 operations can be issued for ALU, 1 branch, 2 load, 1 store, and 3 float vectors in any given cycle. Front end branch prediction and instruction effects. The micro architecture of the MI branch predictor and instruction sketch was convinced, uh, considering three classes of applications: small kernels that fit in micro branch target buffer BTB, moderate size applications that fit in the main BTB, and large applications that get coverage from an L2 BTB. The design of the neural net branches predictions of the micro and main BTBs and inspired by earlier works on pre- uh, Precapton-based branches predictors 3-4. The new challenges for M3 was to keep a wider, more capable machine full of useful instructions. Using a hierarchical approach allows trade-offs between capacity, latency, bandwidth, and power. Kernels with the small footprints can be run in the micro BTB at low latencies, high bandwidth, and low FE power. On M3, the micro BTB capacity was doubled to 128 entries to cover some slightly larger kernels. The accuracy of the micro BTB conditions branches predictors was improved by increasing the local history length, doubling the capacity of weight tables, and tuning confidence mechanisms. As with prior design, the M3 micro BTB includes a loop predictor and a return address tag. Load store unit. The major improvements of M3 LSU can be categorized by the bandwidth improvements, increased out of order capabilities, and capacity latency improvements. One of the large improvements in M3 performance was to add a second load port. This allowed the M3 to support up to two independent loads plus one stored by cycle. Additionally, the transfer bandwidth between L2 and L1 was doubled to 32 B per cycle. The out-of-order capabilities were improved by increasing scheduler depth and doubling the store buffer to 32 entries up to 12 outstanding misses and are supported. Effective data latency was improved by growing the data capacity from 32 KB and 8-way on M1 and M2 to 64 KB 8-way on M3 without growing load latency. The multi-strides pattern prefecture was enhanced and hybridized with a new engine that learn additional types of patterns. The TBL uh, hierarchy was also upgraded, while the first level 32 entry DTLB was two timing critical to grow. A new mid-level 512 entry data TLB was added, and the unified L2 TLB was uh, quadrupled to 4K entries. The core pipeline, the primary core pipe for integral execution and 4 cycle load is shown. The project timing goals to hold frequency despite the design stress from increased width and depth led to trade-offs. While in many areas the team was able to uh, redesign the accommodate the goals. By the end stage were added the net branches misprediction. The pipeline on M3 of 16 cycle is 2 cycles more than the M1 and M2. The DP2 stage was added as a part of routine dispatch to the MOP schedulers and resultant stress on the allocation into those schedulers. The RR2 stage was added to deal with the larger R PRF as well as to better decouple the scheduler loop from the ALU execution loop. The M3 cache heresy. The M3 cache heresy was significant redesign for improved effective latencies and the ability to support increased capacities. Bandwidth links were generally doubled to 32B per cycle at all levels inside CPU clusters. The four CPU clusters used in M1 and M2 with a 2MB shared L2 with a 4 bank BOB3. The configuration in M3 was redesigned with a 512 KB private L2 per core backed by an 4MB shared L3, which are exclusive of the private L2. The L2 is inclusive of the data cache is supported a 12 cycle latency versus the 22 cycles to MB shared L2 on previous design. The M3 L3 consists of a 4 MB shared cache which is exclusive of L2. The L3 cache is non-uniform cache exists designed with the typical L3 across a 25 cycle additional latencies beyond the L2. The silicon performance, while there are many ways to compare performance, Geekbench is an important CPU stress test for smartphones. Combine both IPC gains and higher product size frequency M3 achieves a net speed up on GB V4 single thread of uh, greater than 85% versus M2. Figure 4 shows a Geekbench V4 single thread performance comparison relative to 2.3 GHz M2 versus the 2.7 GHz M3 and 2.8 GHz M2 A75. The power, while the M3 processor technology offered some power relief versus the M2 3 to 5% with the large performance increases demand in M3, it was known absolutely power would go up. The goal of power team was to drive in performance per power efficiencies in the right direction as much as possible using techniques like clock gating. However, at a system level, additional trade-off can come into play. Mobile smartphone systems consist of a mix of big and little cores. The system tends to start tasks on the little core and only migrate to big core when performance demand justifies. It also the system software includes DFS controls that boost and throttle cores as needed as tasks will tend to start at a lower frequency and only get boosted as future performance is demanded. Many users interactivity scenarios only requires boosting core frequencies, which shows a silicon measure GB44 single thread subset comparison of preferred WBTN between M2 and M3 comparable as well as the productive frequencies. So conclusion, the smartphone technology is advancing rapidly and the competition is not standing still. To service the annual cadency of premium smartphone market and to provide the customer with a better experience, expect SARC to deliver competitive CPU performance uplifts and efficiency improvement every year.